Just do a quick recap video of the stuff that we went through on Tuesday when we actually had a lesson. Useful for those that weren't there, but also for anyone to sort of recap the stuff we did. So we're starting a new topic, which is continuous random variables. And a good way to sort of introduce it is looking at the opening problem from the textbook. So you can see that up on the screen. The example is a salmon breeder catching lots of fish, weighing them and recording their weights. Now, their weights are going to be a continuous variable because they can be any weight. There is no set values that has to be. So to record those weights, they needed to be set up with class intervals or ranges. This set was set between 3 kilos and 3.1, then 3.1 to 3.2, etc. As you can see written here. A couple of things to note: when you set those ranges up, there must be an equal to, a greater than or less than equal to, and then a less than, so that there's no ambiguity. If you do have a weight that was 3.1 kilos, 3.1 kilos wouldn't go this side, it would go into this one. Okay. What are we going to do with this? Well, in the past, we could say, all right, we could draw that into a histogram. Okay, so they've drawn a histogram here. Importantly, you can see that there's no gaps between the columns in the graph for a histogram because there's no gaps in the values of the weights of these fish. Now, what I want to do is not worry too much about the mean and the standard deviation. At this point, we'll do that in later videos. What I want to look at is to say, imagine, and you can already see it, we can see a nice curved shape being sort of graphed there. But if we were to make these intervals smaller, then what we would do is end up having an even nicer curve. Now, this one's nicely bell curved. Doesn't mean that real data is going to be perfectly bell curved, but we would get a nice graph that we could draw, and we could consider that as being a function, the function that follows the top of that histogram. Okay. Importantly, the function that follows that histogram, all of the area. So if I actually draw it in, just draw it in like that. If I thought about what was underneath in this space, this area, well, that's all the data. That's all of the weights put there. And so that's like 100% of the data. We can think of that as being equal to, every value must fit in there. If we added all the values up, then that's, everything must be in that. That's really, really important for our next little part. Okay. So using that idea, there's more in this opening problem. We'll come to that in later videos or hopefully in lessons. What we're going to introduce is this idea of a probability density function. Okay. And effectively, what that is just the function that would encompass the histogram that's there. So it could be really nice, like this example here, where it's a nice bell-shaped curve. Okay, and we would consider that what we call normal distribution. Hopefully did some of that last year. But certainly it could be a function that's sort of graphed like this and had a peak at this area here. There was more values found in for that size for whatever reason. Perhaps it's like average or heights of people. Maybe this peak is due to female height. Maybe this is male height's average or something like that. It doesn't really matter. But we don't necessarily have to have a nice, smooth, bell-shaped curve. A lot of the maths that we're going to do is going to use that, but it doesn't actually have to. So we could write a function for it. Okay. In fact, you can write a function for a bell-shaped curve, and it's doable, and we'll actually see it. It's messy. You're not going to have to use a lot of work with it, but there is a function for it. But if these are going to be probability density functions, a couple of things have to be true. One of them has to be that the area that's encompassed underneath the whole function has to be equal to 1. That 1 is means all of the whole of the data, like 100% of the data. Okay, and we're talking about a probability, and we know that we can only have a probability up to 100%. We can't have a probability greater than that. And so what we're saying is that really, if we could calculate the area that you can see shown here from C to D, whatever values they would be, that area is actually going to have to be less than 1. It's going to be more than 0. In this case, it might be about 0.5, looking at that graph. That says that 50% of the data collected fit within the range of whatever C was to whatever D was. So the chances, if you randomly picked one sample, so if this was the fish, okay, the salmon, and I don't know, C might have been at, let's make up a value, let's say C was at 4 and that's at 4.5 kilograms, it doesn't matter, then what that's telling us is that if we randomly picked a fish out of or caught a fish out of the river, there is a 50% chance that it would be between 4 kilos and 4.5 kilos. Okay, obviously, if we extended that range and went right out here to say, I don't know, 3.5, and included that part of the area into it as well, and so went all the way over here, it would be a higher area that's covered in, a higher percentage. So that's what we're looking for a probability density function, what we can use it for. So we've said that the total probability, okay, the area underneath must be 1. Notice our integral sign. So this is good carry on from our last topic, because the integral of that function is going to give us the area underneath, which is what we want. Okay, so the integral from a to b in this here, so from here a to b, the whole function that we've said that's the domain for it, or this function from this a to this b, the areas must equal 1. The other part to make it a probability density function is the first dot point that says that function must always stay above the x-axis. Has to stay above the x-axis, because if it goes below, we're going to get that negative area idea, or we're going to get that negative probability. That's a problem. Can't have a negative probability. Can't have a negative probability a negative chance of something happening. Okay, so to be a valid probability density function, it has to satisfy these two things. And that's what we're going to have a look at, and the questions that were asked for you to do were relating to that. So quickly looking at their example, they've got a probability density function. I told you it's a probability density function. The function's been given an actual value, x squared over 9, and you can see it drawn over here. It doesn't seem like, it's hard to come up with a real life example of what that might be, but what we're saying is that as we get closer to 3, you're more and more likely to get values that are closer to 3 for whatever reason. Okay, can still get a value around 2. In fact, there's quite a few. That it's not that unlikely, but as you get closer to 0, it's less and less likely for you to get those values. Okay, so the first part it's asked to do is to check that it's valid. If it's valid, we have to cover those 2 dot points. So they've done that here. They've said that from the graph, we can see that the function is always greater than 0. Okay, over that domain. So this domain from here to here, it's always greater than 0. All right, and that's what we're only interested in because, excuse me, the domain's given for that function. So a probability density function will usually, in fact, will always have a domain. Potentially has a domain from negative infinity to infinity, but realistically, there's that's the normal distribution. Normally, it's going to be a set sort of nice numbers it's covered in. So firstly, we can see tick, as they've done there, it's always positive. Okay, the second part is to say, is the area under here equal to 1? Okay, to be able to find that, we're going to do the integral. Okay, so the integral from 0 to 3 of the function. Okay, so there's the function, and you can follow through the integral steps and find out that yes, that does come out to being 1. So tick, that's also correct. Those 2 dot points are covered. It is a valid probability density function. Okay, part 2 says this has this sort of notation. It says find P. That P stands for probability. Okay, so this is really saying find the probability that the random variable. And so that's something else to notice, is that we have a capital X used. Okay, so in statistics, if we're talking about a random variable, in this case we're talking about continuous random variables, we give it an uppercase, X, rather than use the usual algebraic lowercase x. So that's saying that our random variable, okay, what's the probability that the random variable, whatever this variable is going to be between the values of 1 and 2. Okay, so between 1 and 2. All right. Now, what that means is really, let's imagine there's 1 and there's 2. Well, what's the area that's encompassed by that space there? That's what it's asking. Okay, so what's the probability of that happening? Really what we're doing is we're finding out what amount or what proportion of the area of this total shape, okay, is encompassed in that little space. Okay, once again, should get a decimal value, has to be less than 1, has to be greater than 0. So it's going to be that decimal you can convert very easily into a percentage. So all we do is do our integral, okay, and this time we're not interested in going from 0 all the way to 3 because that's going to give us the 1. We want to go from 1 to 2. Okay, so we've already done the work. The advantage of doing the work up here tells us that we can, plug into the values pretty quickly, and we get a fractional result. You could turn that into a decimal, you could turn it into a percentage and say what that is the probability, okay? And what is it really saying? It's saying if I randomly took, I don't know what this is a bag of stuff, and if I randomly put my hand into that bag of stuff and took one of these things, the chances of that thing having a value between 1 and 2 is 7 out of 27. That's the probability of that occurring. Okay, so that's what we're looking at. Why would we ever do this? Well, it gives us a good indication of what sort of stuff might be in a population, how big fish might be, what's the chances of getting, a fish of a certain size, how many of the fish or what percentage of the fish are greater than 4 kilograms. Maybe fisheries might use that and say, well, we know this much. We want to make sure we keep at least 60% of the fish population in there. We need people to only keep fish that are bigger than 4.5 kilos, because then at least 60% of the fish are safe and we'll keep that population going. So lots of reasons why you might do it. So just what we might do very quickly is an example of one of the questions I didn't ask you to do, just so it's a different one. And it's probably a good one because it does practice your integrals. It also perhaps you'll see that when we do the integral, we'll practice the logs and e and stuff like that. Not a challenging example. But the first part says the graph that is shown, so this whole graph, okay, is not a valid probability density function. Why? Because of this part here, that is below the x-axis, it's negative. The whole graph itself, not a probability density function, okay? But we could make it a probability density function, okay? And that's what part B is about, by restricting the domain, choosing some values over here so that this area equals 1, okay? And in fact, there isn't just one spot you could do it. If you choose another starting spot, over here somewhere maybe, then you might have to go all the way over here to get that area to equal 1, all right? But we've been told in the question that we want to be able to do it so that the domain goes from 1 up to this value k that we're going to have to solve for. Okay, so we're going to say, well, I know my function is equal to 1 on x, okay? Therefore, if I want to, if I want to find areas, I'm going to do the integral. I'm just going to do the integral here, then we can just plug it in. So 1 on x dx, okay, equals, well, hopefully you remember the rules, it's ln x plus c, okay? And I'm going to use this as a bit of a recap because you still got to do your integration test, remembering that plus c needs to be there. But when we go further, that C is going to die. I'm going to leave it in there and see it die again. But quite often you won't do that for these ones because we are interested now in a definite integral that goes from 1 to this value k. Okay, to find out how far along we need to go of my function. Okay, that's what I want to do, but I know that that has to equal 1. The area under there has to equal 1, so I know this. So, therefore, I've already done the integral work, so it's ln x plus c, and normally we wouldn't write the plus c when we're starting to do this definite integral. Just put it in here to show that it does die again, reminding you. Okay, so we're going from 1 to k, and we know that that equals 1. Okay, so therefore, plugging it in, we've got ln k plus c, take ln 1 plus c equals 1. All right, hopefully, obviously now, you've got plus c and then this negative with this plus c. Okay, we'll cancel it out. So we got ln k, take ln 1 equals 1. Okay, remembering back to our log rules, ln of 1 is 0, so ln k equals 1. To remove the ln, we do e raised to the ln k, therefore k is equal to e, or e to the 1. Okay, so we've got that value. Now we know that if I go back to this stuff here and just clean that up a bit, what we know is that if this was, say, 1, then if we went out here to E, the area underneath is going to be equal to 1. Okay, so we've found that. That's what B is asking us to do. All right. In part C, it's asking us to find the probability that this random variable, whatever it is, randomly picking one of them, but the value is going to be between 1.2 and 2.4. What's the probability of that happening? It's going to be within, this is a bit small, but it's within this space in there somewhere, but not the whole way. Obviously, we're starting at 1. We want to go from 1.2, so it's moved over a bit. So there's a bit of area that's not counted. And E is 2.71, so 2.4 is a little bit less. Okay, so where, the area should be less. Just trying to, if that graph was drawn to any sort of scale, my E is just randomly attributed to nothing much there, but perhaps we'd say it looks like it might be more than 50%, but let's have a look. Okay, so for part C, I'll just write it so we can see it on the screen again. The probability that 1.2 and 2.4, so they're random variables between those two values. Well, it's just going to be equal to the area, or the integral, the absolute integral of 1 on x dx. That's what it's going to be equal to. Now, I already know that that's equal to ln x, okay, 1.2 to 2.4, okay, and therefore it's ln of 2.4, take ln of 1.2, plug it into your calculator, already did it, so 0.693, okay, and on. Probably a good habit, and usually in the exam and tests, it'll say, if it doesn't tell you otherwise, go to 3 significant figures for your answer. So that's a good answer to leave it at 3 significant figures. Okay, that was a brief rundown. All that stuff we had done on Tuesday, but for those that weren't there, and also anyone wants to go back to it, make sure you have a go at the questions. I think I put them up for today's lessons from 8B1, and over the weekend I'll post the next set of stuff up for you to have a look at. Please make sure any questions, send them through. Doesn't matter that we don't have a lesson tomorrow, send them through and I can work on them.